All right, so what I'm going to present today is what we do to make sustainable aviation fuel. As you will see, we cover three main molecules, and two of them are part of particular interest if we want to produce jet fuel and e-jet fuel. So António briefly described it, but what we aim to do at Khimod, so at Khimod we just briefly introducing my company. So we are a French company, and what we aim to do is really to decarbonize those hard-to-abate sectors. We talk here about aviation, but it's true as well for maritime transportation and for some industrial processes. Who we are, primarily we are a technical solution provider, meaning that we propose to the market a technical solution to produce synthetic molecules, gases, and fuels. We are a relatively new company, but we benefit from 20 years of technical development. And the reason why is because we inherited a technology which was developed in another field, and I'll explain that later, which allows us to have today a technology which is fully proven and which has been operational on the ground. We applied that to many pilot projects that I will as well describe, and we have a manufacturing site today. We are about 30 people in total, so and we are mixing process engineering, chemical engineering, mechanical engineering. We have 5 PhDs in the team, so we are moving forward in this area with, I think, the right team. So what we do at Khimod is that our solutions are based on heat exchanger reactors that I'll explain in the next slide. And what we take as a feedstock is either CO2 captured from somewhere, direct air capture, which is more long-term, but point source or biogenic CO2 as of today, and hydrogen mostly coming from electrolyzers, but it could come from other sources. Some people now talk about white hydrogen, which could be another source. So that's a primary way of feedstock. The second way and the second type of feedstock is, and I think we are in the right spot today, is everything which comes from synthetic gases produced from various sources, including gasification of various materials, including bio stuff. And then what we do, and our reactors are they are not exactly the same for each reaction, but they work with the same principles. We can produce with CO, CO2, and H2, depending of the mix, either methane or methanol or synthetic crude. Of course, for SAF, synthetic crude is one of the most obvious paths to refine and then to make jet fuel. There is another path that we are investigating together with some partners, which is the methanol to jet pathway, which has the advantage of not having, let's say, the need to refine what you produce and to have directly something which can be injected into motors. So two pathways for us today for SAF, methanol and crude. So how do our solutions work? All of our solutions are based on an innovative heat exchanger reactor, which is this piece of metal that you see in the center, which basically intensifies chemical reactions by in a reactor where we where we manage it quite efficiently. This reactor is very efficient as long as a reaction is either endothermic or exothermic. And when we talk about methanol and e-crude, which is Fischer-Tropsch reaction mostly, those reactions are highly exothermic, and one key obstacle that you could see is how to extract the heat and how to manage this chemical reaction in an efficient way. In our case, we manage it quite efficiently because, and maybe I can come here, we are on one side, we have reactive channels where we put catalyst and where there is a catalytic reaction happening, and perpendicular to that, we have here thermal regulation channels. Those channels are in the range of a few millimeters from each other. And so by this high proximity, we're able to extract the heat very efficiently and then to manage the heat quite efficiently. And here we generally have a delta of temperature which is generally around 1 degree between the entrance of the reactor and the exit of the reactor. By doing this, this comes with many properties. And those properties allow us to, in the end, decrease the cost of the molecule produced because, and I'll explain why later, but that's basically the main concept is that we are really aiming at decreasing the cost of the produced molecule here. Just one thing, so for SAF, one reaction is of course methanol synthesis reactions that we are able to do. The other, and which then is a brick towards methanol to jet. The other brick and the other pathway, and when you come with CO2 and with H2, is to have a first brick which is called a reverse water gas shift, where you transform CO2 into carbon monoxide, and then we have another brick which is a Fischer-Tropsch, a reaction from carbon monoxide to crude. We manage both of those reactions with our reactors, and this is something that we today are proposing. So our technology comes from a very specific thing which was called the ITER project. The ITER project, for maybe some of you may know it, it's an international nuclear fusion project which aims at replicating the nuclear fusion reaction of the sun on Earth. So it's a very innovative project which started many years ago, and in the framework of that project, there was a need to do the first wall panels of the nuclear core of the reactor, which had to manage a very high thermal flux. And a specific technique was developed in the frame of that project, which is called diffusion bonding. What we take as Khimod is we took all that development, which lasted 20 years, which was developed together with the French CEA, which then in that framework of that ITER project was fully de-risked and let's say came to TRL, a very high TRL. And we took that technique to apply it to something else, which was heat exchanger reactor. So somehow, you know, we benefited from nuclear to do something which is in the framework of e-fuels. What we do is that our reactors here that you see are basically made of various steel plates around 100, and we take them to 1000 degree, 1000 bar. By doing this, we make just one block of a piece of metal. And so this allows us to have a very specific geometry that you will never be able to have with 3D printing or other ways of manufacturing, and which is at the same time something which is very resistant because we can go to very high pressure and very high temperature up to ranges which, to my knowledge, are today not reached in the industry today. So all of that, what does it make? So basically, by the fact that we manage quite efficiently the temperature of the reaction, we are able to reach very high conversion rates of CO2 and of H2. And of course, this has a direct impact on the efficiency of the reaction and on the amount of energy you consume, including the amount of H2 you consume when you do a reaction. As we intensify the reactions, we consume very low levels and with very low quantities of catalysts, which has, of course, an impact in cost. And we are able to develop a very modular solution, which is very useful when you talk about, you know, waste that you gasify, and generally the feedstock is not unlimited, so you are dealing sometimes with rather medium to small size solutions or sites. It's also the case where you extract CO2 from an industrial process. Let's take a cement making plant. Generally, they're around 100,000, 200,000, up to 500,000 tons of CO2 per year. This is rather small when you compare to, you know, what has used to be done in the oil and gas industry, which is generally 10 to 15 times larger. And so we believe that there is a strong need to adapt to sites which are in the range of 100 to 500,000 tons of CO2 per year, which are basically most of the sites that we see today in Europe and in the US. And so our solution is by nature and by the modularity of its design, is totally adaptable to this kind of sites. Then when it comes to methanol and to SAF, our particularity is that we not only manage a very high conversion rate, but when it comes to methanol and for SAF as well, we are able to reach a very high selectivity. And the reason why is because as we control the temperature efficiently, you know, in those reactions, you make the molecule you want, methanol or kerosene, but you make as well a lot of other molecules. And those other molecules basically consume hydrogen, which is the most valuable and the most costly inputs in what you do, and in the end make the solution costly. In our case, we managed to have very low levels of byproducts, which has a direct impact on the final cost of the molecule. Last thing on when it comes to SAF, so we do reverse water gas shift and Fischer-Tropsch. On reverse water gas shift, it's today something which is honestly being developed by the industry. There is no mature technology across the board for reverse water gas shift. The solution we are developing is a low temperature solution. And as you may know, reverse water gas shift is a solution, is a reaction which is very endothermic. So you need to bring a lot of energy into the reaction. And so the lower the temperature you have, the best the efficiency of the reaction is, because you consume less energy and then you are more efficient. And in our case, we develop something which is low temperature, so we believe that what we are developing is quite good. The result of that is that when we put that into models and so on, we believe that we are able to reach a 30% cost reduction versus other traditional solutions when it comes to synthetic fuels. Here, I'm not comparing the cost of what we do towards the cost of what you extract from the ground. I'm comparing what we do towards, I would say, other traditional solutions coming from the oil and gas industry. We basically address that with various angles. I will go quickly through this but basically we are able to provide our reactors, to do engineering studies, and to make solutions end-to-end for small to medium-sized things. This is the size of our reactor range. We are today able to produce what we call a K5 in large quantities. The smaller ones, reactors, are more for chemical reactions in the chemical industry or for some testing labs. And we are able to propose what we call a K10, which is able to address very large size projects. A picture of our manufacturing site. So we have a manufacturing site. We are ready to manufacture. So we take it very seriously. We strongly believe in the methanol and methanol to jet and in the SAF market. And so we kind of broke the chicken and egg dilemma by making the production sites available so that we are able today to produce reactors in an industrial way. Some pictures of what we do. I'll go quickly through this, and a map of fuel references. I just drop by on a few things. We initially came from the methane industry, and so we are able as well to do methane. The most mature projects or the most developed projects today on the ground producing are on methane. We are as well making a project together with a company called Energy to make SAF. It's a project called AVBio, and we are in this project developing a reverse water gas shift combined with a Fischer-Tropsch, and this is where we are developing this reverse water gas shift brick. And just a picture for information on what the type of size and sites we are able today to address. And I think that's it for me, and I'll open the floor to questions if there are any questions.
Okay, thank you. Thank you very much, Nicolas, for this nice presentation. So if there are any questions, please don't forget to state your name, affiliation, and either if you are speaking French or English for the technicians to do the translation.
Thank you. I am Laurent Mou from LNG, a subsidiary of Engie. I have one question. When I see your presentation, it seems to be extremely more efficient to produce e-methane than to produce e-methanol, than to produce e-kerosene. And what we see is that you push all your efforts to kerosene. Are you sure this is the way the market will evolve?
So, yeah, that's a good question, and thank you for asking it. So, the conversion rates are much higher for methane just because the chemistry is it's dictated by chemistry. So there is no magic here. What we do is that we are pushing up to the limit what chemistry and the laws of chemistry are telling us. And by nature, when you do Fischer-Tropsch, there is a cap. And the cap is lower than the minimum that you see in the methane industry. And that's true for us. That's true for any other solutions that you will see today on the market. So there is no magic here. But in our case, what we do is that we push that limit up to the maximum of what chemistry is dictating you. Then we strongly believe on the three molecules, methane, methanol, and SAF for various reasons. But when it comes to methanol, and including methanol to jet and to SAF, this is a market, as you know, where there is a great appetite for those synthetic molecules and for somehow paying what is called a green premium. And the reason, as you all know, and I think is because there is no other solutions today to fly without e-jet fuel or SAF, to fly green, I mean. And so that's a strong belief that we have and that we share. And so we push our developments on the three molecules, and we believe that what we do is a differentiator for those three molecules. We don't do other molecules like ammonia because we see less, let's say, immediate groundbreaking benefits on these kind of molecules.
So, time for another question. Please.
Et bonjour, je m'appelle Sylvia et j'aimerais parler en français, du coup, la question. Et j'y vais tout de suite. Je voudrais savoir si cette technologie a plusieurs, ils ont des références en fonctionnement dans ces moments, ou c'est encore une technologie en développement.
Alors, merci, je vais répondre en français du coup. Nous avons des références en fonctionnement sur le méthanol, sur le méthane, sur le Fischer-Tropsch, et le reverse water gas shift est quelque chose qu'on est en train de développer et sur lequel on devra avoir une référence en fonctionnement d'ici la fin d'année. Voilà.
Any other questions? Maybe I have one question, Nicolas, for you. You state that you can make different types of molecules with your system, with different types of, and you have a catalyst inside for the different processes. So how do you manage the catalyst process? Do you have different catalysts for each type of molecule, or is it done during the project, or is it an in operando solution that you propose?
So thank you for asking this, António. So the way we do our reactors between one reaction to the other is the same. But the reactor actually is not exactly the same, meaning that the channel sizes will be different. There will be, for some reactions, you need more, which are more exothermic, you need to extract more heat. For others, you have less control channels. So it depends a bit of the reaction, and it depends on various parameters, many parameters actually. And we are as well using a different catalyst for each of the reaction. We are not making catalysts ourselves, so we source catalysts on the market to various companies. And so, of course, we use the best catalysts which are adapted to our reactors, which are not necessarily the best catalysts which are adapted to reactors in fluidized bed or these kind of things. So, sorry.
Okay. So if there are no more questions, we'll skip to the next presenter, who is, thank you very much, Nicolas. Please, if you can stay here for the rest of the remaining of the afternoon and for the panel discussion that will start at 5:20, please sit down. So our next speaker is Christer Gustafsson from BioShare. So Christy, thank you. Christy has 30 years experience in the forest industry and energy sectors, spanning from every engineering to business development and investments. He has a PhD in energy systems analysis and is passionate on turning research and development results into innovations in business. We have something in common, Kristen. He's founder and CEO of BioShare, a company created in 2017, who believes co-utilization of biomass and plant assets is the cornerstone to a sustainable development strategy. It proposes transforming large-scale combustion plants into biorefineries and develops technologies and projects for co-production and bio-based fuels and chemicals. BioShare commercializes its technologies as a supplier and as a licensed owner. Christian, the floor is yours.
Thanks a lot. That was a great introduction, covered a bit of my presentation. I'm very happy to be here. This is my second time in Nantes. First time was yesterday, but then I wasn't allowed to land, so I was brought back to Frankfurt. So I arrived here by lunch, and I then recognized, I calculated in my head, I spent 45 hours to come here from Sweden to Nantes. So that is, I could have gone everywhere in the world for that during that time. BioShare is in the combined heat and power business, but we are not really into this with heat and power. So we envision a future where the combined heat and power sector is much more versatile and have much more functionality. So this is our vision picture, showing that a combustion plant could be transformed to create not only heat and power, but to use organic feedstock to create a multiple of energy carriers, chemicals, and BioShare for various usage. Also, we see that it's not necessarily so that power will be produced and exported from a plant. Power can also be utilized and embedded in new products. Also, finally, we see that combined heat and power sector will be able to play a role when it comes to energy storage and electricity surplus. So this is our vision of the future, and we are actively pursuing these paths to create new business opportunities for plant owners and suppliers. In the core of our development is this, what we call thermochemical co-production. And we work there with the fluidized bed technology, and you recognize to the left these dual reactor system set up, where you have one reactor producing heat and another one consuming heat, so to say, in gasification and pyrolysis processes. This could be done integrated then in two ways, either as a separate reactor couple in a combined heat and power plant, or integrated in the boiler itself if it is a fluidized bed boiler. So in short, we work with different ways to realize this. To the left you see a bolt-on, a retrofit solution where a boiler is extended for functionality. You see this, the box at the bottom. This is an industrial bubbling fluidized bed boiler that is equipped with co-gasification equipment. In the middle, if you already in the planning phase foresee that you would like to have multifunctionality, you could include this and have it as an integrated part of the boiler. And finally, to the left, of course, we can do this standalone, and then we are much more free to use whatever bed material, and we could also use electricity for heating purposes to save carbon. I'm here today to talk about sustainable aviation fuel, but I also just wanted briefly to touch the possibilities with BioShare, because BioShare is formed, as you know, during pyrolysis and combustion, and we are in a very thrilling project to drain biochar from combustion processes. So this is something that I mean, there's a separate session of that. It's a nearby solution for negative emissions. So that could really make a change when it comes to the carbon footprint for anyone interested, even in sustainable aviation fuel. And these two are not in conflict to each other. Biofuel production, as you see, we could, basically this is a platform technology, so we could produce gases or liquid biofuels. We could go both via gasification and pyrolysis. Today, I'm going to talk about Fischer-Tropsch as the pathway to sustainable aviation fuel. And I will exemplify this with a study that we have carried out. People around me tend to say, oh, you discover or invent all kind of crazy and genius processes. And I say, it's not my idea. I didn't invent pyrolysis, neither gasification, and certainly not Fischer-Tropsch. It was invented by these two gentlemen more than like 100 years ago now in Germany. So this is not new, and neither is the implementation of the technology. This is the Pearl project in Qatar. And this, I used to say, this is a good example of how it shouldn't look when you talk about biomass, because this is a crazy scale, and this will create all kind of problems if you try to implement on biomass. It was finalized like a decade ago at the cost of $18 billion, so this is a tremendous project, of course, and I think we can agree this is not what we are envisioning when we talk biomass. Rather, it could be something like this. This is a much smaller scale, and this was the outcome of a study we carried out a few years ago, where the output was 30 megawatt of crude, and at an investment cost of 100 million euro, based on a retrofitted district heating plant, producing the feedstock for the Fischer-Tropsch synthesis. And this is, I'm really interested to hear your previous presentation. So I think this is a good match, because we are in the business of providing the feedstock, converting the initial step in the biofuel product. The configuration, not invented by us, you all know, you have gas cleanup, you have shift reforming, and you have the synthesis, and that's it. So what we are dealing with is the integration in the district heating and CHP sectors, both in gas supply, but also in the integration. And looking at the next picture, sort of this shows the power of this approach, because these are already established levels of energy or that you have on site, and these represent an option to harvest any residue heat or streams in the process. So we can capture heat on several different temperatures, and only a minor fraction will go to the ambient. Furthermore, as I said, we can use a very good power situation where there is power available. There is a grid connection which is already in place. So this is the sort of the heart and soul of this integration. Here you see an example of a 30 megawatt syngas reactor integrated with a 90 megawatt boiler. So you see it's a compact installation. It's a retrofit, so it's an external project in the planning phase we are carrying out. And this allows for almost unaltered boiler capacity. It's important to keep in mind, we can't sort of take away boiler capacity. A boiler is there for heat. We always remember that. But of course, there are all kind of like impacts on the boiler on the detail level, shown and exemplified by two of the parameters here in the bottom. Also, very important, you talked about e-fuels here before, and we see that there shouldn't be a conflict in between biofuels and e-fuels. Rather, the contrary, actually, because to keep them separated is nothing but create nothing but losers. So combining high electricity input with biomass resources means that there is a chance for higher carbon utilization and more cost-efficient processes. And it's not a law by nature that you should oxidize your carbon and feed it through the chimney and then restart. Why don't you know already from start what you want to do with the carbon and go that way? And you could utilize, in such a process, you can utilize high amount of electricity in very cost-efficient way for enhancing gasification performance, drive the reforming, as well as supply additional hydrogen. So definitely something we think it's worth looking into. Just a few numbers in terms of the performance. I said before that 30 megawatts and around about 100 million euro in investment. You see the OPEX number, and you also on the bottom, the efficiency as we can capture the residual streams and heat, it goes all the way up to 75%, which is totally unique and defined as the additional amount of energy compared to the additional amount of output from the plant. And greenhouse performance also excellent, around like 12-30% of the fossil fuel. So all in all, a viable concept to enroll, and where you have great cost saving to capture once you go into an already established plant. To summarize, to co-produce rather than to build dedicated plants gives you possibility to achieve higher efficiency. You can also focus on quality. You know that by knowing that all residual streams are captured and made use of, there are savings in the capex, in the opex, and in the flexibility. So strong reasons to look at this way of production. And I just briefly touched now the possibilities. You can freely download the 2 reports describing how we can integrate aviation fuel production, as well as how you can benefit from power usage. So and you either if you take a photo, or you can come to our booth F16 to ask for the link. Yeah, that's it. I have no idea what time it is, but I think I'm within limit.
It's perfect. Thank you. It's perfect. Thank you very much, Christopher. So thank you for this very nice presentation. Any questions from the audience? Please.
Hi, my name is Riyad. I am working in sugar business. How do you think your efficient system will contribute in the cost reduction of the SAF? Because you stop always off FT crude, but after the FT crude, there is also cracking system. So from the A to Z, let's say from the biomass till the SAF, how do you think that you can contribute in the cost reduction in the SAF?
Please use the microphone.
Actually, to date, we have stopped our efforts at the crude. We think that once you have a crude with a proper what's called the English, yeah, with a maximum for the jet fuel, I think it makes sense to transfer this into an already existing plant, creating and guaranteeing the quality of the aviation fuel, rather than to go all the way yourself. At least when we talk about
what is the minimum capacity you can think that FT fuel input to be dedicated to cracker for the SAF? And
yeah, it's quite easily to feed this crude into a refinery and thereby make use of it for aviation fuel.
Thank you. Other questions? I have one question. You talked about your Fischer-Tropsch solution. Do you develop your own Fischer-Tropsch solution, or do you rely on available technologies provided by other companies that provide such technology?
No, we're not developing Fischer-Tropsch technology ourselves. We follow and monitor all new initiatives, and especially those then focusing on small and mid-scale, and we think about how could we harvest the integration benefits, but we are not developing technology in that end ourselves.
Any questions? If not, I still have one other question about the you are using your burners to burn mostly waste. So you have all kinds of feedstocks that come in with different kinds of compositions. When you go to the Fischer-Tropsch, you need some purity of your syngas. So how do you ensure that with the variety of feedstocks that you have, that you are going to have the purity of the gases of the syngas to feed your Fischer-Tropsch unit?
Well, this is a well-known problem. I mean, the more low-cost and more low-grade fuel, the more cleaning of the syngas. And our starting point has been biomass fed boilers. And looking at Sweden, where I came from, there is this sector fires around 10 million tons a year of non-processed woody biomass. So that's a starting point, and we think that there are all reasons to start there. But of course, any waste is interesting, and on certain markets, it's also like society waste is the main source of energy. So yeah, of course, a challenge.
Another question, please.
Yeah, it's related to that. How do you handle the tar problem? Are you getting tar and dust? And also you're using the e-reformer. Who's the provider of that? Because I know only one, but I'm curious to know what reformer technology.
Yeah, e-reformer, that brand name, that is one. I mean, the concept of supplying electricity for reforming could be, I mean, that is an IP question, but we are not developing that ourselves, so we see that as a feasible process solution from a like CapEx and performance perspective. Then when it comes to tar and particle dust, those are things needs to be dealt with, and we have applied a cold gas cleaning, meaning that we scrub the tars away, and we can then use the boiler and the incineration plant for getting rid of any such streams that thereby evolve. So we try to keep it very simple. Robustness is a key.
Yeah, but exactly those two things is a big challenge: dust, tar, and reforming.
Yeah.
Thank you very much. Still time for our last question. Any last question from the audience? If not, please, thank you very much, Christer, for your presentation. If you can, please stay with us for the panel discussion. Please. Thank you very much. Okay, so the next presentation will be a four-handed presentation, I'm sorry. So we're going to welcome Denis ARGUIN, Vice President for Strategic Relationships from ENERKEM, and Zainul ABDIN, Vice President Biofuels for Petrochemicals for Technip Energies. So a few words about our two presenters. So Denis has a BAS on Chemical Engineering and an MBA from the University of Sherbrooke in Ontario. He started his career as Director of Process Technology at Minerals Technologies and has held numerous positions on engineering and operations in industry. He is now Vice President of Strategic Relationships at ENERKEM, a global technology provider of low-carbon fuels and chemical products. Founded in 2000, ENERKEM is the result of a desire to produce biofuels and value-added products from otherwise wasted materials. Their patented technology was initially inspired by research and development on gasification of waste materials and syngas conditioning and transformation into sustainable products. ENERKEM commercializes its technology as licensor, provider of specialized equipment and support services. Zain is a chemical engineering, spanning his professional career for over 30 years in Technip. He was in earlier roles responsible for expanding business for the company in known technology portfolios such as hydrogen or ethylene. He started his career in Technip India office, then worked in Netherlands and in Malaysian offices. Since 2022, he is Vice President Biofuels, Fuels and Petrochemical Markets at Technip Energies. And in his current role, he's responsible for business in the rapidly growing biofuels market and traditional fuels and petrochemical markets. Denis, Zain, the floor is yours, please.
Bonjour. Okay, that's working. Okay, good afternoon. Thanks for the nice introduction, and thanks for the invitation for this conference. So as you can see, we're going to do a team presentation, but not teams remote, teams together, right? So for a change. I'll start with introducing ENERKEM, and then I'll pass it on to Zain, that is going to do the same thing for Technip. This is, at the same time, we announce our new partnership, working together to create a better future, we hope. So we'll go to the slide. Okay, so quickly, ENERKEM, we're about 250 plus highly motivated people. We're a Canadian-based company in Montreal. We have over 120 patents protecting our technology, and we are commercializing the technology. As you can see, we have world-class partners that have, assessed our technology and bought our technology. Obviously, the well-known Shell and Repsol. Maybe for you, a little less known Suncor, but Suncor is the Repsol of Canada. And then you have Proman, which is the second largest producer of methanol. Quickly on the technology, what we do is ENERKEM, what we're looking at is to maximize carbon recovery of waste material. So that's what we're trying to do. So the technology is in the middle. On the front end is the feedstock. We have the advantage with our gasification process to be able to take a wide range of feedstock from obviously biomass, ag waste, municipal solid waste, waste plastic. Preparation of the feedstock is quite standard. It's reducing the size so that we can move it, reducing some of the inert, and when needed, drying. And when we dry it with residual heat from the gasification. We have two gasification steps. Obviously, it's an oxygen-fed gasification so that we don't have inert in the syngas. The primary gasification is a fluidized bed where we obviously mix material, break down the carbon-containing material into a raw syngas, and then remove the majority of the inerts that are not carried in the syngas. The second step, we're going through a thermal reforming to maximize carbon conversion into CO, obviously some CO2 and hydrogen. And then after that, we develop a gas cleaning system. As you here in France, in Canada, we don't have any spec on the waste, so you have to take and be able to clean the waste and the syngas. So we develop a process combining water cleaning and also acid gas removal using chilled methanol to be able to have ultra-pure syngas and at the same time adapt the chemistry or the carbon composition of the syngas before synthesis. ENERKEM, we developed the technology up to syngas and then to methanol. So we also have the methanol technology, and we also develop ethanol technology from methanol. As you can see, we can also enable third-party technology to go to the different market. Right now, we have a project on methanol to DME as a replacement for LPG. Obviously, methanol to olefin is something that is quite used in Asia or in China, not yet in Europe, but for circular economy, it will come. And then you can go, as the former presenter, you can go to methanol to jet, you can go to ethanol to jet, you can go to Fischer-Tropsch as well to jet. So we have those capabilities. So what do we offer? So our advantage is really, obviously, we have a demonstrated and a mature technology. So this is in operation in our facility in Edmonton in Canada. We have feedstock flexibility. So when you build a facility for 25 years, you need to be able to adapt to the market change. As you can see, product diversity, scalability, and versatility for the different feedstock and the change in regulation. The other thing that we do as well is we always customize our solution to have optimum carbon intensive product. So obviously this is quite important in the offering for the customer. Business model, I'm not going to go through that too much, but just to say we have two lines. We have one line that we sell the technology and the proprietary equipment, and the second line is we're developing projects that are what we call FID ready for customer, so to accelerate the deployment of the technology. So just to see where we are, we have a facility in operation since 2017 in Alberta, which transform 100,000 tons per year of municipal solid waste into methanol and ethanol, but today we're producing methanol. Over there we are consuming municipal solid waste biomass from construction, which is contaminated wood, and we also waste plastic coming out from recycling facility. We have a project under construction. It's a $1.2 billion project being put in place in Montreal, on the south shore of Montreal in Varennes, with our partners Shell, Suncor, and Proman, with a lot of support from the local government. This will produce 100,000 tons per year of biomethanol, and with this we have a 90 megawatt electrolyzer that produces both the hydrogen and the oxygen being used by the biorefinery. We have a project in Tarragona in Spain that with Repsol, with whom we got 100 million euro from the Innovation Fund to this facility. This one should go into financial investment decision shortly. And we have two projects with Dimeta for dimethyl ether production. I'll pass the puck, as we say in Canada, to Zain.
Thank you, Denis. And thank you, António, for the introduction. About Technip Energies, well, this is just the partnership we have just announced a couple of months back, and we are working hard to make this thing happen. And that is one of the essential things for the industry to move forward together rather than going and tripping alone. A few words on Technip Energies being a leader in the oil and gas in past. Nobody wants to call oil and gas today. Everybody wants to be part of the energy transition. We also, that's how changed our name a few years back, and moving forward to the energy transition. This is just to give you, and many of you might know already Technip Energies and the credentials of our company, but it is worthwhile to spend a few seconds to highlight. We are headquartered in France, in Paris, in the European Paris Stock Exchange. We are technology based. We have our own technologies based EPC execution company, which global footprint. We have to our portfolio of project execution worldwide of 450 projects at this moment of time. With 15,000 employees worldwide, we do the business with the revenue of over 6 billion. And important thing is that we are there for over 6 decades in the industry, where we have seen too many innovative solutions being implemented, and we have been pioneer to work it out. This is just a global picture where we are present. As you can see, we are scattered all around the world with 35 countries, which provides proximity to global market wherever the projects are.
The two fundamental business models we follow is on the left side of you see is the project delivery, which is the hardcore thing, which means that we make it to the finish line once the FID is there. The projects are built in such a way that it is a long-time operability are there, and they start generating revenue for the owners to live with their business plan. On the right side is also some of the aspects which are key and fundamental to our company is technology, innovation. With our own products, we develop with that, and in that market, we do basically anything from start of concept till the finish line of production and beyond production services. Also, we have some advisory services for customers who are looking for projects to be implemented in any of these fields where we help them in making their program with nowadays also supporting with the digitalization to make the plant digital twin, etc. Most important slide was getting skipped, but sorry. This is what we call it energy trilemma, because energy, the most important thing is that the hunger for energy is going to stay. It is not going to be over, but how to live with it. It is on the left side, what you see is that the traditional fossil-based things where you can do efficiency improvement, decarbonization, but that is not going to be sufficient. So we are also focusing and putting our effort towards the right side of the part, which is sustainable fuel, green hydrogen, and all those circularity aspects of projects where pushing not only ourselves, but also with partners pushing to the limits of the thermodynamics of the equations to bring it to the right way so that the project or the concept which we all are dreaming of is cost effective, because that is the biggest challenge we all are facing today. And it is going to be a hard journey for all of us. It is not going to be over. It will take ages, but okay, we are there to work it out together. When it comes to our energy transition journey, we have looked into, in a hard way, investing a lot of effort and energy in the green hydrogen space, where most of the projects are still struggling to get to the FID, but things are moving and improving, which hopefully will pave the way for the SAF industry, for the e-fuels, etc. We talked about carbon capture. Is easy. Technology is there. Its cost effectiveness is one thing, and then how to make it utilized for the valuable product. That is one another thing to be looked into. In terms of sustainable fuel, and especially in terms of SAF, we are proud to be the leader in executing, implementing projects which are producing or about to produce. And when I say project, it is real project installation, where we will end up soon in 2 years, in 1.5 years' time, with 3 million tons per annum of SAF production, which is unique in the industry. Taking that SAF journey further, it made us start looking into what are the possibilities and what are the things we need to do. I will not go in details, but the thing is that important thing is the blended element of the feedstock contribution into SAF, which is allowed at this moment. That is the key focus area, which means that we all have to collectively work harder to see how to increase these percentages and how to increase the feedstock portfolio as well, which is easy said than done. And as António in his inaugural speech, he mentioned about feedstock limitation, especially when it comes to HEFA process, it is almost exhausted. So how to find it, the adjacent aspects of it are there, but it is not mature or cost effective yet. So the three circles in a dark blue are the technology portfolio or pathways of SAF which are matured enough to run with it. HEFA is exhausted, but alcohol to jet, where we have a technology position for making the alcohol to ethylene, and then with a partnership with LanzaJet, we produce the SAF. And today I'm proud that one of the commercial unit is just completed. Now it is ready for a startup. It will be the first commercial unit for alcohol to jet for producing SAF in the United States. And we are very happy to run further into it. The other pathway, which is very promising and going to be moving forward, will be the Fischer-Tropsch, which earlier speakers have spoken about it. We have taken that journey, and it is a technology of Fischer-Tropsch, which is 100 years old, and we have a good technological relationship with our partner, Sasol, to work on many of those projects in past, and hope to take that journey further. This is a glimpse of where, as Technip Energies, we stand on various projects. I'm sorry for the color coding and the confusion of the different colors with the box and the dots. The important thing is the dot. Green dot is the sustainable aviation fuels dot. And you can see in the global footprint that we are pretty much everywhere in the region of the world from east to west engaged with various aspects of the project, including implementing serious projects. With that, I think I give the microphone to Denis again.
Thank you, Zain. So quickly, I'm not going to go through the detail of this, but as you can see, as far as feedstock and also as far as emission, you see that why we're looking at the hard to abate sector. There are like today in 2014 there were 30% of the global emission, and now it's projected to go at 40% in 2050. As you can see, gasification is at the core of the decarbonization strategy. Obviously in the SAF and the diesel abatement with the gasification to FT or to methanol to jet or alcohol to jet. In the marine fuel with the biomethanol versus gasification, and then in the circular chemical as well, which is not an industry that we talk too much, but it will have to have been addressed as well. So gasification can be used in those different sectors. So, the world is changing and in the right direction, at least from our perspective. There's a lot of change happening toward net zero emission on the greenhouse gas. The key regulation, Europe and the US are pushing strongly to support. You would say some of the carrot, the other one is the hammer, but it's a different philosophy. But both of them are trying to achieve the same thing with different means. We're getting a lot of financial support, and we need to do this because it's a new industry. So we're looking forward to continue that, and there's expanding market. As Zain mentioned, the feedstock for those products is first generation is getting to the limit today. So obviously the EFA and the different material from vegetable oil is something that is ongoing right now, is the most cost-effective solution. But the next generation, we believe that between gasification and e-fuel, those two will play a major role. So, for us, municipal solid waste is, it's a great feedstock because obviously it's available everywhere where there's some people, and it's already collected, so you have all the infrastructure. So if you are able to handle that, it's a good feedstock. And on top of that, it makes a difference because it's also a feedstock that you're getting paid to process. So typically on the facility, it will add about 10 to 15% on the revenue side on top of the final product. So if you are able to handle that, it's a great feedstock. Waste material, ag waste is something that is also of interest. So that's the reason we're pushing hard in that direction. I guess on the aviation fuel, the regulatory platform is there with the European, with the Refuel EU, and you can see the reduction requirement. It's an amazing amount of SAF required. So there's plenty of space for all of the solution, and there's not going to be only one solution that's going to resolve it. So we all have a place to play. With the EU ETS coming in place as well, it's forcing this to happen. And now we're looking at which is the molecule or the product that's going to bring the best abatement costs. And obviously with RED 3 and with the RFNBO coming into place, just as an example, our plant in Montreal, because we're using electrolysis hydrogen, we're producing about 30% of the material is in RFNBO material. So as you can see, the volume are huge. The opportunity, market opportunity is quite important, and you know, regulatory support is in place. EU, you fully appreciate what's being done with the RED 3. In the US, the IRA is putting in place with a huge incentive for SAF. Obviously, in the US, SAF will, a big piece of it will be from grain or corn ethanol to SAF, but the demand is so high that there's going to be more asked. And even in Canada, we're starting to see some regulatory aspect. In British Columbia, as an example, SAF is, the price will be based on $600 per ton of CO2 abatement. So that's quite significant. Then you can make a business out of this. So, you know, how do we compare ourselves? And again, at the end of the day, people will be looking at this as what's my cost per ton of CO2 abatement. That's really how, you know, the industry will be looking at it. Today, as I mentioned, FA is the best material, but it's running on a wall as far as access to feedstock. What we see today is ENERKEM plus methanol to jet is probably very close to FT, but because of the high selectivity of methanol to jet, we believe that is probably a good offer. So it's the next one, and then you see the corn to ethanol plus ATG. The cost is a little bit higher, but there's some incentive that are coming in the US. In Europe, it's not going to play a real role. And then the power to liquid, well, the cost is depending of green hydrogen, and I'm not going to bet on any price. I know how much we pay in Montreal, and it's not cheap. Here you go, Zain.
Thank you, Denis. Just few words as a final takeaway from our messaging is, yes, the SAF pathways, 3 pathways are very much into the right speed to make it happen. But the journey for SAF is going to be very, very huge. And we are also looking like in industry to how to make other pathways go into the next way. The most critical thing, not only because of the feedstock and availability of the power, etc., cost, it's a cost, but also the implementation. Because most of the projects are going to be in the western part of the world, whether in Europe or in US or Canada, etc., Australia. These parts, you cannot implement the project as you do in many other places like a stick built. So modularization is also one of the key things which needs special attention, which puts the pressure up on the business case as well. So we all have to be mindful how to do it. The relationship with ENERKEM, as we talked about, is an innovative technology, well proven. Methanol is already being produced, which is sustainable. We need to take this journey further. We are collaborating, and this collaboration is an example not only for us, but also for others. We need more and more collaboration with all stakeholders, all technology portfolio providers to work together to bring this SAF journey till the end, because it is not a small journey, and it has a major, no single party can provide the complete solution. So we have to be open for that. With that last word, I'll thank you all for patience to have us.
Thank you. Thank you, Denis. Thank you, Zain, for this nice presentation that gave us a very good overlook of different technologies and different possibilities with several types of feedstock. Because our next presentation is at 4:20, we still have time for a few questions from the audience. Please.
Hello. Thank you very much for your presentation. Very nice. Good afternoon. I'm Fabio Paretti. I work at CWEP, which is the Confederation of European Waste-to-Energy Plants. I have two questions, if I may. I will address them in English, but they're actually related. As you touched quite a bit about the feedstock and the abundance of the feedstock, I would like to focus on this aspect. So you said that you can treat municipal solid waste and you can actually replace processes as waste incineration. But you know, as for a practitioner that deals with waste management, municipal solid waste can be very heterogeneous with everything inside. So my specific question is, what is the quality that your input when we talk about waste needs to have, which means how many rejects, how many residues you're generating for refining municipal solid waste into the feedstock? And the second question, which is related, is if you can say something about the project in Tarragona that won the Innovation Fund. What exactly feedstock you use there? Because you said for Alberta you actually use wood waste and some plastics, so not really mixed municipal waste. Thank you.
Thank you for the question. Obviously, you've been there, so it's good. It's good to hear. Just for clarification, in Edmonton, we have three feedstock. Municipal solid waste is the largest. The second is the residue from the recycling facility, so it's high plastic content, about 65% plastic, and the rest is biomass residue. So we've been running for, since 2017 on municipal solid waste. In North America and Europe, we can take raw municipal solid waste, and then we will have, obviously, to remove inerts. So usually, it depends, but let's say 10% of waste is generated in the pretreatment facility. And then usually when it comes to our facility or our unit, we still have about 10% inert in the feedstock. So you're gonna have another 10% of waste generated of feedstock, plus other through the process. So that's roughly what we do. For the quality, so far with our campaigning on feedstock characterization, we don't have to do any selective collection. So as long as we have spec on some of the chemical, but typically, you know, we cannot take PVC as an example full out, but we can take municipal solid waste normally done. So there's no, we characterize through campaign the feedstock, and we never had any issue neither in Edmonton or other process that we ran.
Okay, thank you. There was a question here.
My name is Riyad. I'm working with sugar industry. It's well known that the available or mature gasification in the market working between 700 to 950 degrees C. So does ENERKEM involved or has planned to upgrade this gasification to be working above 1600 degrees C to avoid the issue of tar cracking and using catalytic? This is the first question.
Yeah, good question. At 1600 degrees C, there's no tar, not to worry. So that's why, in fact, we have this two-stage gasification. So the first stage, we crack at low temperature. So at that stage, we have tar and char. Then we're going into thermal reformer up to almost methane extension. So we're trying to convert all the carbon into CO, obviously CO2 and hydrogen. So in our technology, there's no tar and there's no char.
Okay. Second question, is ENERKEM involved in upgrading the conversion to DME, like direct conversion from the syngas instead of using methanol pathway?
No, we're using methanol. We're using methanol. I'm sorry, I forgot to answer your second question. Just remember, on Tarragona, most of the feedstock will be municipal solid waste. We're going to have probably about 10% of B wood, but it will be municipal solid waste that is going today to landfills.
Still have time for one last question. Okay, if not, let us give us a warm applause to our presenters, and if you can stay with us, thank you very much. So, okay. Okay, thank you. So our next presenter is Olli-Pekka Arnio, Sales Manager for Circular Carbon for Sumitomo SHI. And the title of the presentation is Powering a Decarbonized World for Everyone. So Olli-Pekka has a Master of Science in Power Plant Technology and Industrial Economy. After several years as sales engineer, sales manager, and project development director, he joined SUMITOMO in 2023, a more than 100 years old company working globally and providing integrated solutions that support customers from end to end, from inception to design and across installation, execution, maintenance, and operations. He's sales manager and is now responsible of progressing sales projects at the Circular Carbon business line. Olli-Pekka, the floor is yours.
Okay, thanks a lot for introduction. I will start with short story from yesterday. Last evening, our flight was cancelled from Nantes to Nantes from Paris, and we took a cab overnight. It was 6.5 hours because it was electric car and we needed to charge it several times. So we really need biofuels in this world, that's clear. But to the topic itself. So what I'm going to present today, shortly, who are we? SUMITOMO, SHIFW. What we have done in regards of in our history and in regards of gasification, some key references. Then more specifically, oxy-steam gasification and our NSE biofuels demonstration project where we have demonstrated the full supply chain, full value chain to provide SAF from biomass, and then going more specifically for, let's say, a bit more market side and the Fischer-Tropsch part also. So who are we? We are SUMITOMO SHIFW. We are a Finnish-led company, but we belong to SUMITOMO Heavy Industries, which is Japanese massive 6 billion euro revenue company listed in Tokyo Stock Exchange. But we who are Finnish-led company, we are traditionally been with boiler plants and power plants. Our roots are in Ahlström, then Foster Wheeler, and then recently or already several years SUMITOMO. And of course the world is changing. Our history has been in the CFB boilers, big boiler plants, and now during the last years we have been going for several different business areas to change when the world is changing. So we are go through those shortly. So we have this energy generation unit, which is a traditional CFB boiler and power plant business. Then we have this circular carbon, where I am. So we have gasification and carbon capture technologies, services, brownfield projects, and energy storage, also for liquid air power to store electricity practically. So still shortly on the background. So why we have been going to gasification in the end is that we have been market leader of CFB boilers. Decades. We have delivered over 900 big CFB boiler plants all around the world. So that has been the natural synergy and skills in our company to go towards gasification. Okay. So then more to the gasification. So like you can see from the slides, already 40 years over 40 years in that business also. So we started with the air-fired gasification technologies for lime kiln applications, heat and power, the producing gas for heat and power purposes. And then, of course, the latest one you can see in the top here, the NSE biofuels, where we went for steam oxygen gasification with our together with our partner VTT in that case, with catalytic tar reforming and including Fischer Tropsch to demonstrate the full chain, and that plant was operated close to 2 years to really prove the concept. I'm not going too detailed into these all references, but just some listed gasification references. So this one specifically was in Sweden. Something to mention from here. So we have gone, in this specific case, we went for 18 bars in gasification pressure. So we have experience of very high pressure gasification. It has its own devilizing details, so own tricks, of course. Then one other example from Lahti. So this is also a fired gasifier, where CFB gasifier, where different kind of feedstocks, biomass and wood waste type of fuels, bark, construction waste wood, and MSW were used as a feedstock to produce syngas, which is then fired to existing big power plant. And also one more air-blown reference zone here. So this is also waste feedstock based project located in Varkaus, in Stora Enso mill. Before going for the NSE steam oxy gasifier, shortly on the markets. So how we have seen. Of course, we have been, as our focus is in the gasification and syngas cleaning, so we have been looking market pretty widely, and how we see is that these two highlighted for aviation and shipping are the ones most interest market has. So for the aviation, biojet fuel, so going via gasification route to SAF. Also, I think e-fuels, but in terms of economics, by gasification route looks more interesting. Then in shipping, specifically methanol is something we see lots of demand in the market, but that's not the topic today, as we are talking about SAF. Okay, so then jump to the steam oxy gasification specifically. So like mentioned earlier, our concept is based on CFB gasifier, and similarly as in CFB boilers, I think the big value of CFB gasifier is the high fuel flexibility. So it's capable for very varying feedstocks, like was mentioned earlier today, that it's very important to have flexibility for the future, and several markets where clean biomass is not available, so it needs to be based on waste-based fuels. I will not jump into these details to save time, so that we can go for more interesting slides. So this is the NSE biofuels demonstration plant we did in Varkaus together with Neste, big oil company, and Stora Enso forest company. And this was 12 megawatts of CFB gasifier with biomass, and ultra gas cleaning, Fischer Tropsch, everything in between to demonstrate the chain, and this was operated about 2 years. Here is more technical picture of the same. So what we did, we delivered gasifier, then we have a catalytic, ceramic filtering, first syngas cooling, then ceramic filtering to remove the dusting in high temperature, then going for catalytic reformer, where we partnered together with our partner VTT, and from there more syngas cooling, scrubbing, and then downstream compressor and forward was not in our scope, but of course we did that in very close cooperation. So then for ultra gas cleaning, rectisols and Fischer Tropsch synthesis, etc. And I think this is very interesting slide. So like you can see from the right top corner, the availability. So of course the first year was about fine-tuning and adjusting, but 2011 we were able to achieve with the full chain very high availabilities, and that was over a year of operation. So it's with such availability. So as we have seen from the market, all the clients are talking about bankability of this kind of biorefinery projects. So I think this is extremely valid to be able to prove that with numbers here. Here it's a bit same type of picture like earlier, but to show in block diagram the full chain from feedstock up to the kerosene, and what we typically do, and where we see that we need to be to get projects to be bankable, is that to be able to be the integrator for complete syngas island. So including gasifier and syngas cleaning, and we have two different technical concepts there. We have this catalytic solution and then thermal box solution, like was mentioned earlier today. We want to have several technologies, as we know there is different variables, lots of variables in this kind of projects and the feedstocks, etc. And to be able to select the best one from client business case point of view is very important. I think that's where we have done lots of work in terms of also the other value chain downstream from our scope, together with key suppliers in the market, to really optimize the value to client, the high yield, and such the feedstock and high yield and all the OPEX is related to look it from client business case point of view. Here are some tough numbers after all the soft talk. So here we have done, this is of course one scenario, like mentioned earlier, there is so many variables, but this is one scenario of 300 megawatt fuel gasification plant via Fischer-Tropsch route to SAF, and to explain how to read these numbers is that these blocks here are representing the cost euro per ton, including capex, opex, everything, for this complete biorefinery, not only our scope but complete biorefinery based on our understanding on the capex. And then it is calculated so that the project owner gets 10% IRR for the capex invested. What would the SAF price need to be euro per ton? That's the yellow line up there. So we are in a 3,000 euro per ton amount. That's of course one scenario. Yeah, and forgot to mention this was based on the RDF fuel. And then on the other side we have other line where we have added also hydrogen would be introduced to the concept before Fischer-Tropsch after gasification. So that in some cases may increase the business case. Of course, like mentioned earlier today, depends heavily on the price of hydrogen. In this exercise, 3 euros per kilo was used for green hydrogen, but like we know in several cases it may be much higher. So jumping to conclusion, based on the earlier slide, so adding supplementary hydrogen can in some cases increase the business case. I think especially with thermal box reforming, it may look attractive depending on the market, of course, and hydrogen availability, obviously. Then talking about economics of scale, based on what we have seen is that really going for, let's say, big size of projects, 100 megawatt size in terms of fuel is reducing the cost of production. So economics of scale for capex start to bite in for the whole biorefinery, like we have been modeling the feasibility. And then, like mentioned already many times, there is lots of variables. For example, feedstocks, characteristics and availability, hydrogen price and availability. Market mechanisms are different in different locations. In US, for example, biogenic CO2 has a mechanism more in place than in Europe currently. So all of these variables matter. So practically what we are saying is that this earlier slide, it had some numbers, but I think all the cases are different, and we have done our homework together with all the supply chain, value chain, to be able to look it together with our clients and optimize the business cases. So still to summarize, so we are able to include gasification and syngas cleaning as one package in an integrator role, like we have seen is important for the project's bankability. Lots of references in CFB, boilers and gasification, and this proven NSE Biofuels project, together with the fact that we belong to the massive Sumitomo Heavy Industries listed company. These all elements is something we feel that brings credibility for the bankability of the projects. Again, CFB technology allows big variability of the feedstock, and in terms of concrete project size, we are ready to provide up to 200 megawatts per each gasifier unit, and we are able to have several between each, several in line if needed. And for the biomass based cases, we have full commercial readiness to provide this kind of wrapped syngas cleaning, gasification and syngas cleaning plant. And for waste biomasses, of course, we haven't done the exercise like we did in NSE for that, but we have a clear pathway forward how to do it and how to structure it together with partners, so that we can commercially get it wrapped. So thank you very much. That was my presentation.
Okay, thank you very much, Veli-Pekka. We have time for a couple of questions, please. So, any questions from the audience? Please.
This is very interesting, both this one and also the one from ENERKEM. In my past, I've been working with gasification because obviously there's a big incentive to use gasification for my interest is mostly in biomass, and also in this case here we're interested in making syngas for methanol or SAF. But I have actually not been able to find any successful commercially operating plants. So maybe my Google skills are not up to date, but the plants I have, there are a lot of test demo plants, a lot of projects under development. There are also some projects, of course, that's been constructed. But I just hear about huge problems and plants being shut down, relatively new plants. I work with big plants in Sweden, Gobigas, and that was a really beautiful plant, but was shut down after 4 years with quite few operating hours. And there's also a plant in Denmark where I come from. It says it's operating, they call it successful, but it was heavily subsidized, and they run for maximum 2 months at a time. Then they have to clean up everything because dust and tar is just plugging up everything, and the catalyst for the reformer is extremely expensive. So, but please enlighten me. I'm really curious to find some good references because our company is very interested in this area.
Yeah, so I think, like mentioned, this NSE biofuels project in Varkaus, that was really, I would consider, okay, we are mentioning it as a demo plant, but it was 12 megawatt. So I think it's really, we consider it as a commercial plant. It was operated over 1 year. It was proven. It was producing SAF from biomass with high availability over a year. I think from our perspective, that's proven, and we can stay straight and say it's high TRL for the technology. And of course, I think generally it comes then for the if such case develops, it comes for the commercial negotiations and who takes and guarantees what. And when we are willing to, we believe in this project and we are willing to negotiate of these kind of delivery contracts as a company.
Okay, thank you very much. I think that question is very important, and I suggest that we take it for the panel discussion because it's something that concerns everybody in the room. So maybe we can discuss it a little bit later on in the afternoon. Thank you, Olli-Pekka, for your presentation. If you can stay with us for the panel discussion, please. And without further notice, I will introduce our next presenter. Sorry, we will take the questions, the remaining questions at the panel session, just to keep in time. I'm sorry. I'm sorry about it. Please keep your question for the later session. So the next presenter is Gurvan Dano, business manager at HAFFNER Technology. He will present his a presentation on high-quality syngas for SAF production from all types of biomass residues. So Gurvan is an engineer specialized in thermodynamics, heat transfer and energy systems, and he completed his studies by an MBA. He developed a global expertise and high skills in engineering, project management, people management, business development, and sales discussion in the context of industrial energy projects, particularly in renewable energy plants. He possesses a 15-year experience on green energy technology innovation and production projects in the fields of heat, electricity, and gas. An expertise on raw material valorization, such as forest and agricultural residues, development energy-related industrial projects, establishing technical, commercial, and financial partnerships, construction, and commissioning of energy production plants. In 2022, Gurvan joined HAFFNER Energy, a key player in the energy transition for 30 years, designing and supplying innovative decarbonization solutions for mobility, industry, and local authorities. Its technology, based on biomass thermolysis, enables customers to produce renewable hydrogen and gas, as well as other green energies, such as sustainable aviation fuels and methanol. Gurvan manages decarbonation and green gas production projects. Gurvan, the floor is yours. Welcome.
Thank you very much for my presentation. Sorry for my colleagues that I was not able to participate in all conferences because I have a stand and I can't keep it alone. Yes, let's go. So first, why HAFFNER Energy and SAF? Historically, HAFFNER Energy is involved in biomass energy project, in a power plant and heating project for 30 years. For 3 years, we developed and built project in a hydrogen market. And for this, we design our own technology called Inoka. And for to produce hydrogen, we make a design of 0.5 and 1 megawatt syngas production. I will do a conference tomorrow if you want to participate at 2:40 tomorrow afternoon. For 6 months ago, it's very soon, we go to the syngas market. I mean, the syngas market is the direct decarbonization of the industries, direct combustion of syngas for oven or for furnace, and we did a first scale-up at 5 and 10 megawatts. Today we are speaking about SAF, and we will see what is the potential of our technology into this market. So our technology to address the SAF market is called SAF NOCA. And what is the right technology to address the SAF challenge? First, we produce both green CO2 and green hydrogen, the two main elements for SAF, but for other clean fuel also. We are also biomass agnostic. We will see after why for the process. And you can see also the three curves on the right. It's made by the Airport Transport Action Group. These three curves show the SAF production evolution, 3 different scenarios from 2020 to 25. The darker pink is in fact SAF from IFE, so the recycling of used oil called IFE. So we can see that the feedstock is not so important. So it can't match with the SAF in fact demand. The lighter pink is SAF from electricity feedstock, and we can see that in this scenario it will start to grow at 2040 because the same trouble, there is not enough electricity feedstock, and also for this solution they have to find biogenic CO2 to produce SAF. Whereas, in fact, in the Europe has already implemented into its regulation to have 20% of SAF in all the EU airports by 2035. And the evaluation of the US market is around 3 million gallons by 2030. So it's faster and this huge market, and that's why, in fact, HAFFNER Energy want to address this market, because there will be several projects in the next 5 and 10 years. Now we go through our solution and our technology. So the solution for clean fuel is the same for methanol and SAF. Methanol will be maybe more aimed to the maritime transport, for example, and SAF will be dedicated to the air transport users. I wanted to mention methanol because with green CO2 and green hydrogen, we can make plenty of different types of fuel. Our offer consists in a scope of supply and services. But we will not provide all the complete and turnkey project of SAF production. HAFFNER Energy expertise is a syngas production. So we supply a 50 megawatt hypergas module, one or several, depending on the size of the project, on their auxiliaries, for example, the biomass and char, conveying, handling, and storage equipment. We have the automatism, electric cabinet, quite a classic, in fact, mini EPC supply. And also with the service, so the project management, the transport, installation, the code on odd commissioning, and plus the maintenance contract. Let's go maybe to my most important, in fact, slide of this presentation. It's a general description of our technology. How we go to biomass to our high-value syngas called hypergas. And after our we go to this hypergas to SAF. So the green square delimited, in fact, our offer, our technology. The first step is a thermolysis at 500 degrees, and it creates thermolysis vapor, thermolysis steam, and char. The second main step is the gasification of char, which creates like a little bit dirty syngas. And the both stream, the thermolysis vapors and the syngas from the gasification of char will go to the steam biomass reforming, which is like a cracking equipment at 1000 degrees to reach this hypergas. So what is the main advantage of this solution is a strong reduction of tar, which is the main issue of this type of process. And why? We should know that all type of biomass have a melting ash point temperature depending on the type of biomass. For example, wood, it's above 800 degrees, but some cereal, for example, it's sometimes 600 degrees. And if we reach this temperature, the ash, there is a fusion of ash, and this is the main source of tar. So that's why we are below, to start with the thermolysis process at 500 degrees, we are below this temperature. And after we have a cracking equipment, which is like a very fast cracking, so no timing process, which also a long time process. It also permits much to create tars. And the second point is the gasification of char. As we mentioned before, in fact, like biomass gasification is not so easy. Why? Because it's not an homogeneous material in terms of humidity and granulometry. Here, the char, it's like constant 85% content of carbon, and the quality of this char, because of our technology, is like powder. So it's easier to gasify and to avoid, in fact, some main issue of the gasification. So at the end of our cracking, we have like our hypergas. So this is the composition of this hypergas. The two main elements, hydrogen and CO, hydrogen is at around 50%, CO at 39%. And we have some CO2 and methane and traces of other elements. That we can see that there is no nitrogen. Why? Because we don't need air. Pyrogasification, the pyro in Greek, it's fire, so it needs air, it needs oxygen. Thermolysis, it's heating. So we don't need air, in fact, for this process. And we don't want to have it, and we have a specific sealing system by CO2 to seal our technology to reduce at the minimum the air inlet. That's why we have, we think, quite a high-value syngas and a good quality to, in fact, to produce SAF, but to produce methanol or other thing. So it's our supply, and I think after it's more like technical partners. There is a syngas upgrading to have the right ratio to, for example, for the Fischer top, we need to have the ratio of 68% of hydrogen and close to 30% of CO. And after there is a Fischer top and other, in fact, equipment to purify at the right quality required for the SAF. So I mentioned that we are like biomass agnostic because, in fact, of the thermolysis mainly and the fusion ash temperature. And we could accept biomass residues from forest, municipality, agriculture, or industry residues. We can accept clean biomass, for example, straw, flash ice, flash chips. But we could also accept like wasted biomass, like wood clays B. It depends on the content, but some wood clays B, and some green waste also. So to finish some word of HAFFNER Energy, we are like we had other experience in the biomass heating and power plant, but right now for 3 years we are like a small company to try to develop our technology. And for this we did an IPO at the beginning of 2022, and we raised 64 million to develop and finalize on technology and to start the commercial sales. Our technology is sure protected by different patent families. We have already a demonstration site, an operation site at Strasbourg, where we can measure, in fact, our repair gas. We have a manufacturing facility at Vitry-les-François, which is our main office in Champagne area. And we are right now, like me, develop or with other external partners, develop some projects in Europe and in US. And we have also strong partnership, for example, Vika, which is an industrial, and EREN, which is like an investors into the technology or into project. So here to finish, it's like some project, mainly that we did before in our old story, in biomass cogeneration plant, for example, in Italy. It was a 15 megawatt boiler, 15 electrical steam turbine. We valorized pumice oil. In Netherlands, also in Amsterdam, we make an EPC for a cogeneration biomass plant in the port of Amsterdam. So we have a strong experience, in fact, in also in engineering and EPC contract, and sure in different type of biomass valorization. Thank you very much.
Thank you very much. Thank you very much. Thank you very much, Gurvan. We have time for a couple of questions. Please raise your hands, and Gurvan will be happy to take the questions.
Merci. Arthur Clé-Renaud, La Batte Énergie. I'd like to ask if it's possible to make SAF from biogas, like coming from a digester, like 65% CH4.
Really, I can't answer to this question, because HAFFNER Energy, we are more specialized with cellulosic biomass, you know, and the valorization of this to produce syngas. Maybe there is another pathway, maybe some people know, but me, I don't know, maybe, but I'm not sure.
Okay, and what's the moisture content, maximum moisture content of the feed?
So in all this type of process that we see today, we have to be, before the gasification, the thermolysis or pyrolysis, we have to be between 10 and 50% humidity. After, we can have recovery energy into the process itself to have a dryer to dry. Us, we can accept close to 30% humidity maximum, because we can recover energy to dry this biomass before the thermolysis. But if we have biomass up to 30%, it needs to have an external dryer and external energy also to dry.
Thank you.
Just before taking the question, I think Matteo wanted to react to the first question.
No. Just a question about.
Oh, sorry. So there was. I think there was someone before.
So I will answer that question. Yes, okay. You can convert the biogas to SAF, There's two technology in the world. One is with electrical, it's Caffenia. So you'll take the CO2 and biomethane to the bioreactor. It's working with electrical, and you'll produce adjusted syngas, H2 and CO. And there is another technology in the world, thermal technology, is sun helium. You can take the biogas to the reactor using heat from solar or any other sources, and you can convert it to FT technology, FT crude.
Okay. Thank you. Please, Matteo.
Hi, hello. I'm Matteo Betti from Italy. I'm working in Alfa Laval. I will give a speech late after you, but
Yeah.
I'm curious to see because I'm quite new in the sector. I mean, I jump into this SAF production and recently, but it called me the attention. The olive pomace. I mean, you have a project in Italy where you use olive pomace to produce.
Yes, not with our technology. It's that I mentioned.
Yeah.
It's the whole story of HAFFNER Energy. We were involved in engineering and EPC contractor for power biomass plant, cogeneration biomass plant. Okay. And in Foggia, it was to valorize pomace oil, sansa.
But the fat in the pomace, or you use the wood? What is it that is interesting for me to understand? Is the oil that is in the
the sansa virginic.
But you burn it completely, or you just separate the oil?
We have to extract some water before because it can be very humid, depending on the oil process. But yes, it was sansa.
Fantastic.
In fact, in this project, it was a boiler. The biomass boiler can burn sansa.
Yeah, sure.
But at the humidity maximum around 40-45, you have to take off all the water. And yes.
So it's not to produce SAF, but it's to just produce energy using the biomass.
Yes, to produce steam and after electricity. Yes. Great. No, because as I said, it's not so easy to gasify or to transform, in fact, some material to syngas. And I can answer to you also that, in fact, there are some projects working. We are like, in the first 2 demonstration plants, we made some operating run, but there are some operating plants, some competitors, and it really is dependent on the use and the quality of syngas. For example, there are some project working for production of electricity, so to burn syngas into gas engine. The quality of syngas has not to be not so high, but it's working. Some project is working.
Okay, so thank you very much, Gurvan. If you can stay with us for the panel discussion, thank you. Let us give a warm applause to Gurvan. Thank you very much. And our final presenter of the evening, actually there are 3 presenters for the next presentation. First one is Matteo Betti from Alfa Laval, Lee Dobinson from BIS VIRIDI, and Harry Hunter from BIS VIRIDI also. So just to introduce them, Matteo is an agriculture engineer and food process technology expert. He developed his expertise in more than 20 years working in Alfa Laval, starting his career as process engineer. His main competencies in decanter technology applied in different food industries, and recently he focused on the introduction of the new decanter oil plus in vegetable oil, animal proteins and food waste. That's what the presentation will be about. Lee is a recognized expert on the anaerobic digestion process, specifically of food waste, and a leading figure in the industry with over a decade of experience. Focused on client service provision and waste optimization, he is responsible for developing and delivering bespoke waste strategies for clients up down to the UK. Lee now heads up the growth of BIS VIRIDI, a new company part of the Biotech 4 group, the leading anaerobic digestion operator in the UK. Lee's role is to drive the sales, oversee the management of the kit integration, and analyze the key metrics in partnership with Alfa Laval. Finally, Harry has graduated with an MSc in renewable energy. He is responsible for planning and refining the process and equipment ancillaries, and budgeting as well as troubleshooting installations of the patented process for oil separation across anaerobic digestion facilities and working closely with our partners in Alfa Laval. Harry's job is to assist integration at anaerobic digestion sites across the UK and overseas, instilling confidence in using the equipment, adjusting it to tailor to each site as required, and leveraging the return of investment for customers. Matteo, Lee, Harry, the floor is yours.
Well, good afternoon to everybody. I mean, this presentation is about how to produce, to increase, to give our contribution to the SAF market by producing a good feedstock. And this experience came from a partnership between us as Alfa Laval, that we are a global provider for solution basically in 4 different areas: sustainable food, clean energy, energy efficiency, and circularity. I think you heard about us in the energy area. I work for Decanters, that is a part of this. But what I would like to underline is that the driver for us to contribute to this circularity concept is to through the partnership, and this is exactly what I'm going to talk about, because this experience started from a customer need that comes from BIS VIRIDI, that is. Lee will present himself later, but they came up with an idea to how to differentiate the stream in their facility where they treat food waste, and how to convert the food waste into valuable fuel feedstock. Alfa Laval is a company active in heat transfer, separation, and fluid handling, and I'm basically working in Decanters, and all these projects started into this area of Decanters. I give the speech now to Lee, that will present BIS VIRIDI.
Good afternoon. So BIS VIRIDI is part of a group of businesses whose core is processing food waste through anaerobic digestion. We operate a number of different facilities across the UK, and we're processing, we believe, more than anybody else in the UK, around about 550 to 600,000 tonnes of food waste per annum. We were born in 2012, and over the years developed into the business that we are now. Essentially, this project was born from a desire to diversify the outputs from the anaerobic digestion industry, particularly our business. And you have to remember that in the AD industry, you are very much a price taker. So the biogas that you produce, you sell either as biogas or you sell as electricity through CHP. And that really is our 2 revenue streams. So our desire was to try and diversify our outputs, give longer life to the AD industry after the incentives have finished. So we partnered with Alfa Laval to develop a process to extract the oil content, or at least some of the oil content, out of our incoming feedstocks and monetize that and create a new value stream. So we now have a global player in technology solutions and decanters, along with our core business, which is a key player in the anaerobic food waste digestion process. And so over the last 3 years, we brought both the experiences between those 2 teams together, and we've developed a turnkey project in order to drop into our AD facilities and start to extract that high quality oil. If we look at the scalability, we essentially have a situation now where we've installed 4 decanters into our facilities across the UK, and they're able to be now just dropped into situ and turned on. Now, if we look at the wider marketplace, there's somewhere, well, you can see from the slide, there's somewhere around 2.5 billion tonnes of food waste being produced globally, and we can't find anybody that is currently doing anything like this type of technology. So they're tapping into that food waste oil and separating it out for better remuneration through the production of green used cooking oil. And where we're seeing our particular interest is in both the biodiesel and what we're here to talk about today, the SAF markets. Because the oil is being produced from waste, we see a real interest in the refineries using that oil to develop into SAF. So it's a really large market that we've got that we're able to tap into. Not only that, but it's able to attract those accreditations and that certification from the renewable space.
Yes, and how we contribute, I mean, as I said before, they came to us and asked a solution to improve the revenue in their AD plant. And we have recently developed a new decanter that is exactly designed to maximize the extraction of oil from any oily feedstocks. And this is the reason why I asked you before about pomace, because I think pomace has a huge potential. Because until now, you know, you burn it or you just extract oil by solvent, but a good way to use it is to differentiate and to extract the oil to be used as a precursor or as feedstock for SAF. And we have developed this decanter that is basically a skimmer, and it's a new design, has a particular design, conveyor design that is able to maximize the oil extraction. We have applied in several applications, but we are also introducing in other areas where we have oily feedstocks where the oil extracted can be also used for SAF or for biofuels. And this machine, you feed the decanter with a soup that contains oil or fat. And from one side, you get a clean, very clean oil, very high quality. Then Eric can give you some insight about the quality of the product we get. And from the other side, you get a slurry that can be sent directly to the digester or wherever, or to a second extraction step. We can get out of this machine more or less up to 100% of the free oil that is contained in the feedstock, with a purity of 99.5. So it's extremely good product. And this is how we install the machine and how we have installed it. We have 4 units running in UK, and of course. Each application of the machine is tailor-made because it depends on the way the anaerobic digester plant used to treat the feedstock. But in principle, the idea is to have it after the hydrolysis and after eating up the feedstock that it's, in this case, is food waste. But as I said before, it can be also pomace, for example. We take a part of the stream, we separate the oil, and we send back the slurry directly to the digester for the methane production. I give the word to Harry, that is the oil technical manager in BIS VIRIDI. He can give some more technical details on the process.
Hi everyone, my name is Harry. I'm the technical manager for BIS VIRIDI. So the pictures really say 1,000 words, so we'll go through that. So the picture in the middle there is a breakdown of anaerobic digestion. Irrespective of how an anaerobic digestion site is laid out, whether it's post-digestion pasteurization or pre-digestion pasteurization, these 4 stages will be happening: hydrolysis, acidogenesis, acetogenesis, methanogenesis. In the 4 examples that we have live at the moment, we've targeted acidogenesis, okay? And that's because in acidogenesis, the conditions are, as you might expect, acidic, which is one of the 2 requirements for successful separations. You need acidity and temperature. It doesn't have to be acidogenesis, it just helps, because you can almost guarantee acidity. If it happened to be in hydrolysis, which in some cases, in some site layouts, it would have to be, not necessarily a problem. The picture on the right here, again, says 1,000 words, I think. So the bottom picture there is a spin sample of some food waste AD feedstock. You'll see solids at the bottom, that orangey layer is liquid, and then that brown layer at the top there is the oil. That accounts for about 5% of the feedstock in this example. The picture labelled return, That's after it's gone through the Alfa Laval decanter. And you'll see that brown layer has gone. And the top picture there is the oil once it's been separated. We aim to put this process in so that it doesn't affect the existing AD system. So whether the machine is on, off, down for maintenance, whatever, the AD process continues to run in the background. This is a parallel process. And the idea, really, is to diversify the revenue streams, because AD, like Lee has said, it's limited to gas export, electricity export, and I suppose digestate export as well, which is a biofertilizer. The equipment that Alfa Laval offers is what you see here. So it's on a skid. It's about 3 meters wide and 9 meters long. Probably quite comparable with this stage, actually, for those who can see it. Everything you need is on that skid. Pumps, flow meters, sensors, control panel, the centrifuge. It's all on that skid, ready to be delivered to site and installed. Hence why it's called a turnkey solution. For more commercial information, I'm going to pass back to Lee. Forgot about this slide. The product properties, so the oil itself. In our case studies of the 4 sites that we have running, the M&I, the moisture and impurities, it's 99.5%. So for the refineries that we've been sending it to so far, it's more than adequate. FFA is about 15 to 20%, again, in terms of what it could be and what other industries have, adequate. Sulfur, 75 to 100 ppm. They've got no problem with that. Energy density, which is an important part of sustainable aviation fuel generation. So if your source material has a low energy density, by the time it's been refined, you're not going to get as much work out of that fuel. So you would either need more fuel, or you would need, or you wouldn't be able to go as far in an aeroplane. So the energy density of the raw material that is produced from this process is about 32 gigajoules per meters cubed, unrefined. So by the time it has been refined, I would expect that be about 10% higher. When we consider what SAF is in terms of energy density, we're nearly there. It's about 35. So by the time it's been refined, we're about where we need to be for sustainable aviation fuel.
So if we think about things from the anaerobic digestion business's perspective, it needs to be viable and both commercially and economically for them to produce the bio crude. And so we put a slide in here to show how that works. So if we take a few assumptions for a second, the average food waste processing facility in the UK is processing around about 80,000 tonnes. Now, in our feedstock, across our facilities, we see around about 7% available oil. And I've also assumed the gas price as of 2022. So I'm trying to give you a pessimistic view of the world. Gas price in 2022 was very high. And we also saw a fairly low oil sale price. So both of those assumptions are in here. We've also accounted for all operating costs, downtime, et cetera, running the skid, including man hours, et cetera. So if essentially, I can talk about this in more detail with people who want to, but if you do not replace the feedstock, because it's important to understand that when you take out some of the oil out of the AD process, you obviously reduce your gas production from the AD plant. So you have two options, because it's also important to understand that any AD plant is capped on its outputs. So be it biogas down a pipe, or indeed electricity through a CHP, both of those channels can only accept an amount as a maximum. So you have one of two options. You either replace the feedstock that you've removed, or you do not, and you see a reduction in income from gas. If you don't replace the feedstock, then our case saw an extra 640,000 pounds. So what's that? 830, 850 euro per annum EBITDA. However, if I did replace the feedstock, then Actually, the business case to the AD plant was a further £1.3 million, so 1.5 euro, additional income to the AD plant, as well as diversifying our income streams, which is particularly important. So it achieved the brief that we initially set out to cover. The other thing to consider is that it's now able to attract those accreditations. At the time, we weren't getting an income for things like ISCC certification because at this point, this was a brand new product in the UK. We had to go through the certification process with bodies that had never seen this before. We've now gone through that certification process. We have the accreditation, and so we've seen an uplift in income of around about 10 to 13%. So it's highly sustainable.
Just to conclude, I mean, this solution is proven. I mean, we have been able to prove that we are able to separate it to get out oil from food waste, and this is an advantage in differentiating stream and getting more value. The solution is integrated with the AD plant, and you don't need to interrupt the production of biogas. And it's important to remember that this kind of technology, this specific decanter, can be also applied in other areas where you need to extract oil from oil feeds. So it's not only for food waste. This case has been proven in the food waste, but it's also, as I said, pomace or animal subproduct or whatever. We have some oil in the feed. It can be UCO, for example. And this machine is really effective for the purpose. It's applicable in any AD facility with fat and oil. And of course, we are able and open to give our collaboration for find a tailor-made solution with customers that are interested in getting this new stream in the market. Thanks, everybody.
Thank you very much, Matteo, Lee, and Harry. Thank you for this very insightful presentation on how to get a new feedstock for the production of SAF, which completes the panel that we've seen: CO2, bio waste, plastic waste, residues, biomass. Thank you very much.
Yeah.
So we have time for a few questions.
What is the pH of the produced oil from this chemical process?
Quite low, I think. Do you remember?
In our examples that we've had in the UK, it comes out at about 4.5.
4.5. So it's better than the pyrolysis bio oil produced. So 4.5, do you think that you can crack it alone in cracker, or you need to blend it with other oil to crack it?
You mean in the refinery?
In the refineries?
Yes.
Unfortunately, I don't know.
It's relatively low pH. That means you cannot send it to dedicated refinery to crack it in SAF or biogasoline and other. You need to blend it with other oil to crack it. And this means that this project is not feasible unless it has big size to be dedicated refinery for the project itself. This is the issue that you.
Well, if it needs to be blended, then it can be blended. I mean, what we can remember as well is that the energy density of the material is high enough that it was to be blended, it wouldn't impact the final product. You'd still end up with a useful end product.
Yeah, but this is not the only story. The pH is one of the main parameters, whether you need to blend it with other oil for the refinery, or you can dedicate a standalone refinery to crack this oil. So your life now, it will be linked to the other people to produce the final product. From the
Of course it will. I mean, it was always good. This wasn't a final solution to the problems of SAF. Like some of the gentlemen up here have already said, it's going to be a combined effort to find a solution to the problem.
Yeah, I think just to to give a compliment. You can use it in co-processing because the co-processing way, if you take animal fats, there is a co-processing way that is certified by ASTM, and that can give you a 10% inclusion rate. So you can co-process this oil with the fossil streams and reduce the CO content of your final kerosene. Any other questions? We have time for one final question before the panel debate. Okay, if not, let's
I think it's really important to understand that the people in front of you here, we're experts in anaerobic digestion and experts in decanters. So this event is as much for us to understand. So your questions and the comments that you make are really very important to us because it's our learning is in your direction, just as yours is in ours. And so I think that's the value of events like this, I think.
Okay, thank you very much. Let's applaud our presenters. And well, there's only one seat. Maybe we can add 2 chairs for the other. Oh, okay, or you can stand up, or we can stand up. Okay, so we thank you very much for your attention. So we come to the end of this session, and we have a few minutes for a panel discussion, as said. And before taking any questions from the audience, I would like to start with the follow-up of a question that was asked a few minutes ago about the industrial viability of the facilities, of the number of projects that have been born, that are being built, but also projects that are being closed. How do you think about it? Maybe I don't know. Maybe Denis. Please, one of you can start.
I can start. I think it's a question with many answers. One of them is, of course, the market. Was it ready by the time? I think many projects were driven from a technology push and market and willingness to pay wasn't really there. Also, I think that many projects was like created as an island, as a technology in a vacuum, not paying sufficient consideration to the energy system and the independence and the interaction possibility with heat and with power. So I think in order to be successful, now is the time, and also the insights of how the devil is in the details. And I think there are good chances for making it this time.
I think gasification has had pretty bad days over the last few decades, right? Project. When you start from gasification from coal, which has always the same feedstock every day in, day out, hours, and you go to a different feedstock, it's a big adjustment that you need to make. So yeah, there's been some failure. There's some commercial plants that are running at lower scale. I think to your point, those projects, because of the feedstock, because of I would say also the biofuels, and those are pretty complex, and you need to have the right partners to make it happen. It's not a technology provider that will make it happen, and it's not a producer of fuel that will make it happen. It's the combination of all of those above. So I see the future pretty good in that direction.
Maybe one of you can want to add something. Nicolas, maybe?
Yeah.
No? Please.
If I may add,
sure.
I think what we have seen in last 4 or 5 years in the industry, the projects when people were conceptualizing, they were industry in rush. We were conceptualizing on the ISBL portion of the project. When I say ISBL, it is inside battery limit of the core unit. What we were failing to do is to understand what happens to the logistic of the feedstocks, the off-site and utilities for the facility, because those things can be even more complex in terms of monetary value and business case proposition. And that's what was making us collectively fail in pulling the project forward. Now, industry have learned, and people are starting to believe, and realistic sort of project estimation with the right scoping those things have started to happen. So I hope we can understand and take learning in going right way.
Okay, thank you. Nicolas, please.
Yeah, just to add one thing. We are not making gasifiers, but my takeaway here is that, first of all, the fact that the industry has been somehow working on it for the past 20 years is a very good sign that, you know, things are really about to work and are already working in some areas, which is quite good. And I'd be afraid to have something which has never, you know, where this experience has not been there. The second thing is that let's take the problem reverse. I mean, we all need SAF, right? And I think we all agree on that in this room, I guess. And so there's not so many pathways. I mean, there are a few, and the feedstocks is limited. It's either like waste, so any type of waste, or CO2 and H2. And the way we look at it, I mean, everybody talks about H2 at €2 per kilo. The reality, if you look at Europe, is that it would probably be the lowest at €6-7 per kilo, maybe. And so this would drive some kind of high cost. And if you look at all the solutions that were presented here, they all have the benefit to get rid of that dependency. And that's, I mean, so there is no other way to make it work. And I'm fully confident that this will work full scale. And I'm not opposing one pathway to the other. I think somebody mentioned it, but we need everything. So.
Okay, please.
Yeah, thanks. I could continue from the market point of view. So like you said, the SAF market is increasing heavily. Based on my understanding, I think if there is people from oil companies, you are more specialist, but generation 1 projects like food-based fats, it's very limited amount of projects in world where is feedstocks and infrastructure in place for such projects. So anyway, the market demand exceeds the potential of generation 1. So we need to go for generation 2 gasification route. And I think in regards of risk sharing, it's about finding, like colleague here said, finding right commercial partners and negotiate to find an arrangement where risk sharing is reasonable to get the project bankable and forward.
Any other comment?
Yes, a little bit. I think the three in fact subject is the preparation of material. Some technologies will accept only, you know, the same material, very clean and very well prepared. And if it doesn't the case, if in one the project you have different type of materials, you have to have the technology to treat these materials, and this is the main issue. And after, I know that some projects that we mentioned, it's maybe sometimes also the cleaning of the syngas, which is not linked much with the users. And there is, yes, material, the technology, and after the syngas upgrading is also very important to have the right syngas, because us, we produce a pure syngas, for example, HAFFNER energy, but to have the right ratio of hydrogen and CO, it's made by others. So it's to find the right partners also.
Please, go ahead.
It's brilliant to see all of these industries making innovations in their industries to create SAF. It's really great to see. I'm proud of our contribution in anaerobic digestion. Again, just trying to innovate new ways of increasing sustainability. In terms of what we're doing, I'm proud of where we are, and I hope that the contribution that we can make, hopefully globally, as well as all these guys' contributions together, we can really fill that hole that's in the SAF market. I mean, we're in early talks with Neste, with Qantas Airlines in Australia, and that's just on our side. Where these guys are at in their process, I think we'll be able to hit our targets for the SAF demand 2030, 40, 50, all the way on to 2050, where the process at the end there with hydrogen. By the time we get to there, hopefully hydrogen will be a much easier thing to generate, a much more cost-effective thing to generate. So it's exciting.
Okay, any questions from the audience to the panel? Okay, I have one other question. When we talk about SAF, we mostly classify the different paths in terms of CO2 gains, in terms of yields, in terms of facility to have feedstocks. But one thing that we don't see much and that you presented in your presentation is the cost compared to the carbon market. We know that the problem of SAF is, well, it's mostly looked at in Europe, in the US, not much in the world outside. And both in Europe and the US, there's a carbon market. And one of the first times that I see a presentation showing comparison of the cost regarding this carbon market. So how do you see it? How do you see this comparison between the different pathways? For you, Nicolas, also, for example, that you propose different pathways. Do you do this kind of calculations? Do you do this kind of estimations in terms of cost to show to your clients what is the best solution for them in terms of product that you are going to produce compared to the carbon savings that they make in terms of ETS, for example?
So short answer is yes, we do. No, I guess Technip has much more elaborated models than we have, but yes, and it really depends of the context. I mean, you know, we see a lot of different contexts where one solution makes sense somewhere, doesn't make sense to another place, and so it really depends of many parameters, I would say. But it's true that Europe and the US are providing a clear framework which is useful for what we do.
Yeah, maybe just quickly, I think at the end of the day, we're all trying to reduce CO2 emission. So you need to, you know, baseline what's your solution, what you can bring it, because if it's too high, it's not going to work. So you may as well know it early in the project. So, but this is a new thing, even in the maritime and the SAF. People are not all there, but it needs some explanation and discussion.
Yeah, it's a complex business. It's a complex issue because ETS is recently applied to transportation, to air transportation and maritime. So the reflex of comparing your solutions with the ETS, for example, is not straightforward, and it is not very historically has not been done much. I hadn't seen the kind of slides that you've shown at the end of your presentation. That's something that I haven't seen much. So I was curious about your thoughts about it.
No, António, I think one thing is showing the trend, because there will never be a perfect calculation to bring the thing. But collectively in our industry, what we need to be mindful of is that we have a big challenge to meet the SAF production goal. So we should not pull the chain to stop the train. We need to let it go. So, and all processes needs to be promoted and projected and taken the right action to bring the things to right solution.
Someone else
wants
to react?
First, I understood your question to identify the most economical path to reduce carbon.
Compared to the carbon cost.
And that goes for certain sectors, but there are also specific demands for certain sectors, meaning that there is not one solution. There needs to be several solutions. Another takeaway that I think we should think about is that historically biofuels and sustainable fuels, we have seen the carbon, the raw material, as source of both the building block and the energy. And in reality, it doesn't have to be the sole source of the energy. It is the building block, but energy could be supplied, because after all, SAF is stored energy.
Anyone wants to react? Yes, please.
Yeah, thank you. We've talked a lot about biomass to make SAF. Do you need to actually add H2 to make SAF from just pure wood, or do you need to add some more waste or the feeds?
So it's not compulsory to add. I think if we talk about our technologies, we have two different kind of tar reforming systems, and both have pros and cons. And other one, especially this catalytic one, you get okay yield just without adding H2. And then for box, it may be more attractive to add hydrogen because the CO H2 ratio is different between the options. But I think you can do it without adding hydrogen. In some cases, it may look attractive from business case point of view, but I think it's very case dependent from economics point of view.
Okay, and next question. Do you work in Africa countries, in Central Africa?
Well, I think if you ask us to go as an EPC there, it may be a bit challenging, but certainly we can deliver something.
Thank you.
Me, I can answer also to a question, because you see in our syngas we have more hydrogen and a lot of CO. And yes, some project developers think about to produce hydrogen with electrolysis and to consume all the CO to maximize the SAF production. So yes, but you need to have a less cost of electricity, and this is the main, in fact, issue for the electricity feedstock and green.
Well, if I can just add something, if you take biomass from a carbon to hydrogen yield perspective, then regardless of the cost of the hydrogen, you would be interested in adding hydrogen just to take advantage of all the carbon available in the biomass.
One question here. Hello.
Yes, please.
I work for a bioeconomy cluster in France, and I'm seeing that there are sometimes constraints regarding the biomass availability for many kind of bio-based products, and can be also biofuels, mainly for SAF fuels, that we need to consume a big quantity of biomass to produce more than 80,000 tons of SAF. What do you think about there's people from different countries, but what do you think about biomass availability in Europe? It's possible to achieve the targets with the biomass competition also, because it could be used for different kind of biofuels or other kind of bio-based molecules. Thanks.
Wants to react?
Yeah. For reaction, I have not all the answers, but in terms of biomass from wood, it's more in the Nordic countries that it's very interesting in. For example, if I take in France, the ADEME, in fact, want to push the actors like us to go more to the agricultural biomass residues, because biomass residues from forest activities will be more for eating, for district heating, or to decarbonize with the boiler, some industries. And after, there are also biomass residue from industries, from agriculture industry, which can be very interesting. Yes. So we have many, for example, in France or in Europe, in Spain, that in HAFFNER Energy we are looking, because biomass from forests in France, yes, it's quite very hard to develop this type of project, because the quantity is very, very important.
I think in the long run, it's important to remember that for now, the main consumers of biomass is the combustion sector, and they use the biomass without using the biomass constitutes in their product. They are just using it for their captured energy contents. So in the long run, if there is a shortage of biomass, those will not be competitive, because there are other ways to produce heat and power. But for carbon-containing materials, you need carbon.
Yeah, I would say, biofuel is not the only use of biomass. So I think those big challenge that we have, you need to look at different sources. So as you said, this ag waste is very important, that is not being used. Municipal solid waste is another one that is biomass. So you need to look at a wider spectrum.
Just wanted to add something about the biomass. I would be happy to discussing with you afterwards. The biomass problem is actually it has to be taken care of, but what you have to see is that there is not enough biomass to replace all the SAF. That's obvious, but there is a lot of biomass, and the problem today is not how much biomass is available, is how to aggregate the actors around the biomass to make them understand that they can take value out of the biomass that they produce, and especially in terms of agriculture and the forest residues. One last question. I have just one last question about regulations. 2023 was a very rich year in Europe in terms of regulations, in the US also. The things are getting much more clear in terms of possibilities to have business cases, reliable business cases from biomass. What is your, maybe each one of you in very shortly, what is your point of view about regulations? Are they enough? Is there something still to be done to clarify? What is your point of view about that, please?
I think what happened in last year was more than necessary to make this industry start. And with that regulation, we see that the economic actors are not pushed enough towards finding real and concrete solutions. Now, what is probably now would be the next step is how to secure the large amount of financings that are at stake and everything around warrantying and guarantees around those large amounts of monies. And everybody talks about investing in SAF. Now finding investors which are truly investing millions and hundreds of millions of euros at a reasonable IRR into projects, it's another story. And I think that's the next step.
I mean, we could talk about legislation that has been the main question for so long now, and all the time there are changes and some things get better and other things get worse, and but there seems always to be an uncertainty about the future, so I think more to be done.
Okay, but do you see more clearly today, or is there still a piece lacking in the puzzle?
No, I think one can see clearly for now, but in the long run, I think we are seeing not technology neutral, really legislation. They are like pushing some solutions and restricting other solutions, and on top of that, you have the sustainability, which is constantly redefined in a way. So, of course, there are challenges.
Okay, thank you.
I think, as you said, 23 was a great year because it elevated the regulatory environment. You got US and Europe that are more inclined. For the financing, I agree, but now they're talking about contract for difference, which is going to be extremely helpful, because when you want to finance those projects that are $500 million or euro, you need to have strong financing. But I think there's always more to come, but it's very encouraging what happened over the last 12 months, for sure.
Okay, thank you.
It has already been said that positive direction, but still some improvement points are there. And the biggest hurdle indeed is the project financing, because project financing needs assurance from banks or the lenders, which are to the extent which is unacceptable for the industry as a construction or implementer of the project. So those hurdles are becoming more problematic, and that's why the FID are shifting towards right, and we need to do something collectively to help that process.
Yeah, thank you. I think to raise one thing, if we go to the other side of the big lake, to the North Americas, it's I think generally the legislation has been a bit in front. So for example, how the biogenic CO2 is recognized exactly. So I think that is, and that's why I think we see lots of projects more developed in North America than Europe. Though it's very important that we will be in line in terms of this.
Yes, I agree that, for example, in US they are technology neutral, In fact, they have, I think, more financial process than in Europe. For example, in Europe, green hydrogen, for example, at the moment, it's only hydrogen from electricity. Because in Europe, we would like to choose the technology, and it's a problematic for hydrogen production. At the moment, we are like in a hole, and so we are like in a hole also for the financing, because if it's not really defined in the EU regulation, after the European will not finance the project. So I think there are some work in Europe. I think in US it's easier.
Okay. Thank you.
To look at it from a slightly different perspective, one of the biggest issues I see in regulators is they're hugely under-resourced. So the human resource within the regulators is really very stretched. And so the knock-on effect that it has to industry is that it prolongs time, it increases the length of time that decisions need to be made, which then gives you a problem with investment, and it gives you a problem with innovation. But then you see it becomes a self-fulfilling prophecy, because the people that are left in the regulators are under a lot of stress and a lot of pressure. And actually the best people within the regulators get enticed by the likes of the people that are in front of you here, because actually the industry and commercial environment is a better one and more lucrative. And so the best people within those industries, we end up seeing in our own businesses, tying the people that are left in the regulators up in knots, and in turn creating a longer problem. So actually, if we did nothing different in the regulators, but just give them better, more experienced resource, I think we would see a major change.
That's an interesting point of view. Thank you very much. Okay, so just to finish up this session, thank you very much for your attention. We have seen this afternoon that there are I think the most important message is that there are a lot of technologies available. Feedstocks are available, and you have seen a panel of technologies that are able to transform those feedstocks into something useful that can lead to SAF later on with the right technology. So today we have the technology, we have the regulations that are more clear today than they were before. We have the resources, we have the feedstocks, we have the technologies, we have industrial sites that also need to be adapted and that can be adapted to new areas. There are a lot of things that we have not discussed this afternoon, but we didn't have time for everything. But the landscape is much more clear, and I hope that you've seen this afternoon. So I'd like to thank all the panelists, all the presentators. I would like to thank you for your attention, and give a warm applause to everybody that participated. Thank you very much.